we're going to be doing an FRQ for Unit 4 of AP Physics 1. So, a group of students has two blocks, Block A and B. Block A has mass MA equal to 0.1 kilograms. Block B is more massive than Block A, but its mass MB is unknown. The students wish to experimentally determine MB. As shown in Figure 1, the students have a long horizontal track along which the blocks can slide. Friction between the track and the blocks is negligible. The students have two photo gates, which can measure the speed of the cart at a certain position, but no other motion sensing equipment. Describe an experimental procedure to collect the data that would allow the students to determine the value of MB by making a linear graph. Provide enough details so that the experiment could be replicated, including any steps necessary to reduce experimental uncertainty. So, let's first start off by discussing what we know and what we don't know. So, we know the mass of MA, and that is 0.100 kilograms. And on the other hand, our unknowns are the mass MB, and also we know that we have a frictionless track. And we also know that we can have two photo gates which could measure speed. In addition, we know that the blocks collide on the track. So using these ideas, we can use the conservation of momentum during the collision. So we know that if Block A collides with Block B, then we know that P initial is going to be equal to P final. So to describe our experimental setup, we can write that first we want to place Block B at rest on the horizontal track. It's actually here on the track. Second, we want to place Block A a short distance away so it can slide toward Block B. After this, we're going to utilize the photo systems. Use the photo gates to measure the speed of Block A just before collision. And what you'll measure will be VA initial. Fourth, we want to allow Block A to collide with Block B. After this, we want to use the photo gates to measure the speed of Block B after the collision. So now we have VBF. After this, we repeat the experiment several times to reduce our random error. And we want to have ensured the track is level and also that the blocks are aligned in the same way for each repetition to reduce systemic error So again, what we know is that because friction is negligible, that means that the horizontal forces are negligible. External horizontal forces are negligible. So that means that momentum is conserved, which means that you have MA VA initial is equal to MB VB final. And since we know MA, we can, and because we measured both of the speeds, then we can determine MB. So here we have these. Part B. For the data collected in the procedure from Part A, describe how students could create a linear graph and how the graph could be used to determine the value of MB. So, up here, well, we can write MB is equal to MA VA initial divided by VB final. Okay, from Part A, we start out with MA VA initial is equal to MB VB final. Now, rearranging this for VB final, we have MA over MB times VA initial. And we can see that this matches the linear form of y equals to mx, where y is equal to VBF. We can just highlight this. Y is going to be our VBF. MA over MB, that is our slope. And VAI, that is our x. So we can construct, we can construct the graph, which would be first to plot VBF on the vertical axis. Second, we would plot VA initial on the horizontal axis. After this, we would plot multiple data points from our repeated trials. After this, we would draw a straight line of best fit through the data. And then we would use the slope. We would use our slope to solve for MB. Use our slope. So have our slope, we know slope is equal to MA over MB. So if we were to solve for MB, MB is equal to MA over the slope. So, in conclusion, by plotting the final speed of block B versus the block A, then we can create a linear relationship, right? And then the slope of the graph is equal to MA over MB. And since we know what MA is, the block of MB can be determined from the slope. So, let's see this. The following day, the students are given two carts, cart 1 and cart 2, as shown in figure 2. Carts 1 and cart 2 have masses M1 and M2 respectively, both of which are unknown. The students wish to determine the mass of M2 of cart 2. They also have a collection of blocks that are identical to block A, each with the known mass MA is equal to 0.1 kilograms, which can be attached to cart 1. A spring attached to the inside of cart 1 can be compressed and used to launch the carts in opposite directions as indicated. The students conduct a number of experimental trials in which the number of blocks attached to cart 1 is varied. For each trial that the carts are pressed together, compressing the spring and then are released. The speeds V1 and V2 of carts 1 and 2 respectively are experimentally determined after the carts are released from rest. The table shows the results of the experiment. Okay, so we have the table here. So we can see these are the varying number of blocks. These are the varying number of V1 speeds. And then these are the V2 speeds. So the student correctly determines that the relationship between V1, V2, and M2 is given by V2 over V1 is equal to M1 over M2 plus N times MA over M2, where N is the number of blocks attached to cart 1. The students create a graph with V2 over V1 plotted on the vertical axis. Indicate which measured or calculated quantity could be plotted on the horizontal axis to yield a linear graph whose slope could be used to calculate an experimental value for the mass M2 of block 2. You may use the remaining columns in the table as needed to record any quantities, including the units that are not already in the table. Okay, so we have that our vertical axis is V2 over V1. And what we want is a relationship. We want a linear graph, right? So that just means that we're targeting the form y equals mx plus b. So we can start by rewriting this equation that we were given here, right? So if we rewrite that equation, we have v2 over v1, which was already great, right? So we have m1 over m2 plus n ma over m2, right? We can actually move the n here, make it look a little nicer. So now that it's written out like this, we can clearly identify that it really matches like this form, right? So we can see that y is equal to this. We can see m1, that is there, and mx, or we can see m, and then we can also see x here. So we see, y is the ratio of v2 over v1, x is equal to n, m1 over m2 is the y int, and we see ma over m2, that is our slope. Slope, y int, y, and our x. So what we can write so we have our vertical axis is y2, so that's y. So our x, that's going to be n, number of blocks. So what this question is asking, even though it seems a little intimidating, it's just asking you to decode. They already gave you the equation. You just have to decode which parts of the equation are corresponding to what parts of the axis, right? So let's move on to our next part. On the grid in figure 3, plot the data points for the quantities indicated in part C1. Clearly scale and label the horizontal axis, including units. And then draw a straight best fit line for the data graphed in part C2. Okay, so let's actually pull this data down here. Okay. So now we can start by using the table. Yes, so we would put, for our horizontal axis, we have n, right? And we have v2 over v1 for our vertical axis. And then we can label the axis with the units, but our units, the ratio is unitless, and n is number of blocks. Now we're gonna plot 5 points. So at 0 blocks, we have v1 over v2. So what we can do is we can calculate v2 over v1 for each trial. So this is going to be 1.06 over 2.20. That's going to be 0.48. If you type this into your calculator, this will be calculator active on the College Board. You can do 1.5 over 1.35 over that's y, that's x. So you're just going to do y over x for your m. V2 over v2 over v1. Right, so then you have 1.35 over 1.5, that's going to be 0.90. You can have 1.17 over 1.38, that's going to be 1.18. And then you're going to have 0.94 over 1.52, that's going to be 1.62. 0.77 over 1.6, that's going to be 2.08. Now we can write the exact coordinates for these points. So we're gonna have, for our graph, we're gonna have x, y. What we're gonna be graphing are points in this form. N versus v2 over v1. So we have 0, 0.48, 1, 0.90. We have 2, 1.18. We have 3, 1.62. And we have 4, 2.08. Now, how do we draw these axes? So we have a scale for this. We have 0 to 4. And we want equal spacing. So it's going to be like 1 unit per. And for our vertical axis, that was unitless. We're going to start at 0 and go to 2.2. Okay, so let's see here. 0 to 0.48, that's going to be approximately like here. We have so 0, 1, 2, 3, 4. Okay, 1.9 right here, 2, 1.18, 3, 1.62, and 4, 2.08. So if we draw a line of best fit, we can, that would approximately be like this. So it would roughly pass between 4, 2.1 and also 0, 0.5. Calculate an experimental value for the mass of block 2, M2 using the line of best fit line you drew in part C. Okay, let's see. What we can do is we can define the slope. So our slope, we can just use approximately 2 values from the data that we have here, right? So we can do 2.08 minus 0.48. Just choosing 2 points here. We have this point and this point. 4 minus 0, and that's going to be 1.60 over 4, 0.40. So this was 0.480, and this was 2.084. Okay, so now we remember earlier our relationship involving slope. Slope is equal to MA over MB, right? So solving for M2, we have A over slope. Now, plugging in our values, M2, we have 0.100 over 0.40, which is 0.25 kilograms. So, that's your answer.